Finally, the last learning sequence in the main part of this course is about non-parametric methods. And you remember that we discussed already non-parametric methods in the very beginning, in the first learning sequence, where I have shown you how to use non-parametric methods for describing your data. And there we learned how to use median, quartiles, quantiles, percentiles, and so on and so forth. But now let's talk about how to make an inference using also non-parametric approach. So therefore, I highly recommend you to rewatch the very first learning sequence, block 1, learning sequence 1, just to refresh all this knowledge about it, how parametric methods work, and then come back to this one, or just continue. Okay. So this is the plan. Let me start with introduction and tell you why actually you need non-parametric methods, and then we will consider several very common non-parametric methods, non-parametric tests, and also the ways to compute confidence intervals. Okay. So what you see on this plot is actually a performance in quizzes in this statistic class that I actually took from one of the years. It was 2 years ago, as far as I remember. And then you can see it's a performance for block 1. Okay. As you can see that this is a percent of correct answers in the quizzes. And you can see that distribution of this percentage is very, very uncommon, right? So we used to some central tendency, we used to this distribution. It can be skewed distribution to the left, it can be skewed distribution to the right, but here the distribution is completely unexpected, right? So you can see that you have a lot of people who have very low number of correct answers, and then you have a lot of people who have very high number of correct answers. Even if I remove all zeros, assuming that these are students who didn't have a chance to take a quiz, even in this case, I don't see a very clear, for example, skewness issue, right? In this case, we still have this U-shaped distribution, and apparently we cannot use the methods that we have learned so far. For example, if I want to compare distributions from 2 different years, which year is better than the other year, right? Or maybe if I want to find out if the average correct score, the percentage of the correct answers is, for example, above 75 or below 75. So I cannot do all these kind of things using the parametric approach, because simply parametric statistics will not be reliable in this case, right? If you look at the box plot, you can see that this little dot here, it's a mean, and this is, you remember, it's a median, right? And then you can see they are pretty far away from each other, and also you can see that the box is very large while the whiskers are quite small. Okay, so in this case, you cannot use all these methods that we have learned. Actually, you can, but they will not be very reliable. They will not provide you a reliable result, a reliable answer, right? So this is the case exactly where you need to use non-parametric approach. But however, it's not always necessary, because sometimes you still can use parametric methods, all these tests that we have learned so far, but you need to transform your data, and that's what we will start with. How to transform your data so it follows a particular distribution. But if it doesn't work, then you need to use non-parametric methods, and this is the main topic of this learning sequence. Okay, so let's start with transformation. What is transformation? You simply take your values. For example, you take these scores, the percent of correct answers, and apply a certain mathematical function. For example, it can be logarithm, it can be exponential function, it can be square root. You apply any function that makes these values follow, for example, normal distribution or any other theoretical distribution. So instead of original values x, you produce transformed values y, assuming that the transformed values will follow a distribution. And then you use y instead of x, because you always, for any function, for most of the functions, you have an inverse. You can, for example, make a test and compute confidence interval for y values, and then use inverse function to compute it for x values, right? If there are no outliers in your data, then simple transformation like logarithm or power-based transformations, we will discuss them a little bit here, will help you, okay? And actually you have used already one, I will remind you in a minute. But if you have outliers, or if transformation doesn't work, for example, in the previous case for this percentage, the U-shaped distribution, I don't think we can find a transformation that will work. So in this case, you need to use also transformations, but applied on rings. So you need to compute rings first, and then use transformation on rings. Okay. So let me show you a couple of examples for the both approaches. Approach number 1, you have no outliers, but distribution, for example, skewed, so it doesn't show you this clear a central tendency. So let me show you, first of all, let me remind you that we already have used this approach. When we computed sampling distribution for correlation, for Pearson correlation coefficient, you remember that it doesn't follow, especially when correlation is close to plus minus 1, then it's very skewed. The sampling distribution is skewed. So if you take a lot of samples and compute correlation of the samples, this correlation distribution will be skewed to the left or skewed to the right, right? And what the trick we used? We used a transformation, right? We used what is called Fisher transformation, where based on R, we computed a special statistic, which is called Z prime. And this is how we computed. So we simply used a natural logarithm of ratio, where we took correlation plus 1 and minus correlation, and then took a half of it. And then we found out, actually not we, of course, it was Ronald Fisher who found this, that this transformed value follows normal distribution. Not precisely, but it can be well approximated by normal distribution, and then the standard deviation, in this case of these Z prime scores, will be 1 over square root of sample size minus 3, right? So you already used transformation, and it helped, actually. So now let's talk a little bit more, just a couple of more examples. First of all, the main transformations that you can use if you have a skewed data, if you have a skewness, are logarithm. Most of the time it's natural logarithm, but you can use actually logarithm with any base. The square root of value, the inverse square root of value. And then if you think both square root and inverse square root, it's actually a power transformation, right? So what is, for example, if you write y equal to square root of x, it's the same if you write y equal to x in 1 over 2, right? Or x in power 0.5. And then if you write y over 1 divided to square root of x, it's the same as x in the power of minus 1 over 2 or x in a power of 0.5. So you can see it's all these are kind of power transformation. And there is a general transformation for the cases like this. It's called box-cock. So this is how it looks like in general case. I wrote you only when lambda is not equal to 0. When lambda is equal to 0, then it's just a natural logarithm. But if lambda is not equal to 0, it can be negative, it can be positive. Then you can see that it's a x in the power of lambda minus 1 divided to lambda. What is lambda? Lambda is a parameter that you need to manually tune. Just simply tune this lambda until you see the normality. For example, if you want normal distribution, and then you will get the transformation that you need. Okay. So let me show you an example. So this is my data. I just generated randomly this data set. This is x values, 200 values, so to make distributions look nice. And then you can see that the values are heavily skewed, right? So you can see you have a very heavy tail on the right. And what you see as a red curve here, it's a theoretical distribution, normal distribution. So I computed average value, I computed standard deviation of this sample, and then I tried to show how theoretically this distribution should look like if indeed it follows normal distribution. And you can see it's far away from normal distribution, it's heavily right skewed. Now look, if I make a distribution of logarithm, natural logarithm values, you can see it's much more symmetric. We still have, in this case, you can see that now it's left skewed a little bit, but the degree of skewness is much smaller, so it's almost symmetric. If you take a square root, then it's even better. You can see it's still a little bit heavy on the right, but again, much more symmetric than we had the original one. And then you remember, what is square root? Square root is x over 1.2, so it's x over 0.5. So if we change this 0.5 a little bit, so if I use Box-Cox transformation, then you can see I used lambda 0.2, so it's a little bit less than 0.5, right? So you can see that it's almost ideally symmetric in this case, and then indeed it follows normal distribution. So if you check, for example, normality, you will see that it passes the normality test as well, okay? So that's the easiest way to deal if you have data which does not follow any distribution, but you want to use the parametric approach. So in this case, if it's just skewness, if it's just a problem of skewness, use transformation, and then you know that for any function, you have an inverse function. So use transformed values, compute confidence interval, make a test, and then recompute the confidence interval back for the original values if you know the inverse function. Okay, so this is the easiest way. Now, what to do if transformation doesn't work? Or for example, if you have outliers, because outliers can spoil the data set quite a lot, right? But again, of course, you can say we can remove outliers, but what if you can't? What if these outliers are not just, accidentally wrong answers? Maybe you indeed have these results and they are meaningful, so you cannot just remove them, right? So from that point of view, this is, again, I'll show you this image. So this U-shaped transformation, it's clearly, you cannot find a transformation that corrects this U-shape, right? Probably you can, but it will be very difficult. So what to do in this case? Well, in this case, you need to use transformation based on ranks. So first you compute rank of values, and then you use ranks instead of the values. And again, let me show you an example. The simplest probably example ever, what is called Spearman correlation coefficient. So we still talk about correlation. We know Pearson correlation coefficient, which is standardized covariance, right? What's the difference between the one that we know, the Pearson correlation, and Spearman correlation? The difference is very simple. Spearman correlation, it's a correlation computed for ranks. So first you compute ranks of your x and y values, and then compute the normal correlation coefficient, right? So what it does, first of all, it removes slightly the problem of outliers. And second, it allows you to work with non-linear trends. If you have non-linear trend, monotonic trend, it's important, it's monotonic, it doesn't go up and down. But if you have, for example, trend like this, so you can see it's monotonically goes up, or maybe something like this, so it monotonically goes down, but non-linear like this, right? So in this case, the Spearman correlation will be a very good way to estimate how strong this trend is, although the trend is not linear. Why? Well, as I said, the procedure is simple. Use first compute ranks for x, ranks for y, and then you compute the Pearson correlation for x and y, and then let me show you an example. So in this case, you can see that I have a data set with 10 values. So it's people. You can see 10 different persons. For every person, I know two values. It's height and weight of this person. So this is height and this is weight, right? Then you can see that I have height and weight for every of these 10 persons. So if I make a plot of these values, you can see that although there is a clear trend, right? So between height and weight, but this trend is non-linear in this case. You can see this is the curve that explains this trend. It's monotonic curve. So it's monotonic trend, but non-linear. So if I make a linear fit, you can see that points will be scattered quite a lot around this line, imaginary line. So therefore, the normal Pearson correlation coefficient is not a good idea to use, because Pearson correlation coefficient works well when you have a linear trend. But if I compute ranks, for example, this is the smallest height, this rank number 1. This is next smallest, this is rank number 2. Then you have next smallest, and so on. When you see this 7.5, it means you have two values, and therefore they have the average rank. You can see 170, 170, right? So let me make a plot for ranks. So this is height, but ranks, right? You can see from 0 to 10, from 1 to 10, sorry. And then this is the weight for ranks. And then you can see what happened. It stratifies your dependence, right? So you don't see this curvature anymore. You see it as just a linear relationship, right? So if you compute correlation for this case, the correlation will be higher than comparing to this case, just because correlation is about linear relationship, right? So let me show you calculations. So first I enter the data set. It's simply I enter these two columns. And then I compute ranks. In R, you know that there is a function that computes ranks for any variable. So I compute ranks. And now if I compute correlation for the values, for height and weight values, right? You can see height and weight. You can see the correlation is 0.76. Not very high, right? But if I compute correlation for ranks, and you can see I use the same function, so it's Pearson correlation, but computed for ranks. You can see it's much higher. It's almost 0.87. So from that point of view, using ranks, because it stratifies the relationship, gives me a more reliable estimation of how strong this relationship is. Because in this case, the relationship is nonlinear, and Pearson correlation doesn't work well. Now, actually, because it's very common statistics, Spearman correlation, it is built in R. So instead of computing ranks, you can skip this and let R do it for you. This is how to do it. You simply compute correlation for your original height and weight values, and then you add additional parameter method equal to Spearman. And in this case, this function core will compute the Spearman correlation. You can see that it's the same as we had before, right? You can see it's the same. Okay. So that's the basic idea. However, it's not always, it doesn't always work just computing something on rings. Of course, strictly speaking, you can make a t-test on rings, you can make ANOVA on rings, and so on and so forth. But it's not always a good idea. So therefore, we have also another option. We still compute rings, and then we compute a specific statistic based on the rings. And it is known that this statistic follows theoretical distribution. It's known because statisticians actually have proved that or have checked that. And then you can use this theoretical distribution for this particular ring-based statistic to make a test, to get a p-value and so on. But of course, in this case, you cannot compute confidence interval because it's rings. It's not the real values, right? So how this works? Well, this is what is called a non-parametric test. So it's a test based on this ring-based statistics. I decided to select, there are many different non-parametric tests. I decided to select probably the most common ones. So for example, when we have a test for one sample, for example, we test for a mean, like if lake is contaminated or not, in parametric approach is student t-test for mean, right? That's what we have learned in the second learning sequence. Non-parametric approach, in this case, it's called Wilkinson-Sinet rings test. When we need to compare two samples, again, in parametric case, you compare means of two samples, and therefore you use two-sample t-test for means. In the non-parametric approach, you cannot use means, you should use ranks, right? And there is a test which is called Mann-Whitney U-test, which tells you how close distribution of rings are. Then if you have more than two samples in parametric world, we use ANOVA. The non-parametric analog of ANOVA is called Kruskal-Wallis test. And then finally, these three are tests. So these are tests. So they can provide you a p-value, and then you can use a p-value to make a decision. But they do not provide you confidence intervals because they are all based on ranks. And you remember, confidence interval we compute for a particular characteristic of your sample, right? So in this case, for example, you can compute confidence interval for median or for the difference of medians. But these tests do not provide you this possibility. However, there is a workaround. There is a very nice method for computing confidence interval for anything, which does not rely on any distribution. And this method is called bootstrapping. And that's what we also will cover in this learning sequence. Okay. So let's start with one sample tests.